In this Hess's law example, we're asked to calculate delta H for the given reaction between N2H4 and H2, which produces 2NH3. And we're given three balanced chemical equations and their corresponding values of delta H. And our goal then is to manipulate those equations in such a way as to give us the top equation, a desired equation. We'll notice that the first reactant in our reaction, N2H4, appears in the third of the given equations and is in the desired amount. That is, it has a coefficient of 1, which is exactly what we want. So we're going to keep that third reaction exactly as it is and leave the enthalpy value unchanged. The second reactant in our reaction, H2, appears in the first given equation, but it's not in the desired amount. It has a coefficient of 2, and we want it to have a coefficient of 1. So we have to divide that reaction by 2, and whatever you do to the equation, you have to do the same thing to delta H, so we'll also divide the enthalpy value for that equation by 2 as well. So that gives us 1/2 of minus 572 for delta H for this new form of the equation. The product in our reaction, NH3, ammonia, appears in the second equation, but in this case it's neither in the desired amount, that is, it has the wrong coefficient. It has a coefficient of 4 rather than 2, which is what we want, nor is it listed as a product. It's listed as a reactant in that second equation, and we want to get it on the right side as a product. So we not only have to divide the equation by 2 to get the right coefficient, but we have to change the sign and reverse the reaction. So we're reversing the reaction around, going from left to right instead of right to left, and we're changing the sign on the corresponding value of delta H. So the adjusted equations are given here along with their corresponding values of delta H. If we combine those three adjusted equations, that is, we'll add together all of the reactants in all three equations, and then we'll add together all the products in the three, we get a fairly complicated looking equation, but we can combine similar substances to simplify a little bit. It gives us this equation, and then if we cancel out substances that are the same on both sides of the equation, we get a fairly simple result. We get exactly the equation that we wanted, which is the correct equation. Now that we've added the equations together, Hess's law tells us that if we add these three equations together to get our desired equation, then the value of delta H for our desired equation is the sum of the delta H's for the three equations that we added together. We can simply add those three values of delta H together to get a sum of minus 142 kilojoules, which is then our final answer. That is the value of delta H for our desired reaction.